Welcome to the Talking the Talk podcast, where we'll be exploring items of automotive technology and their journey into mass production. I'm Kevin Reid, the founder of Ireland Made, where we celebrate stories of Irish transport past and present, and this is our podcast. I'm delighted to welcome my co-host, Automotive Engineering Consultant Mike Keane. Mike's consultancy delivers bespoke and sustainable transport solutions, and previously Mike has led vehicle development programs for Ford, Williams Formula One Advanced Engineering, Nissan, Jaguar, Land Rover, and Aston Martin. Mike has also worked on projects as diverse as hybrid supercars to off-road electric vehicles. But what is most impressive for me, Mike worked on the James Bond movie Spectre, and he worked on the baddies car, the Jaguar CX-75. In each episode, we're going to be examining vehicles that range from the 1921 German Rumpler right up to what Tesla and Lucid are doing today. Hello again. In our previous episode on the origins of transport and the move into mass production, Mike Keane and I chatted about auto styling. Today, our subject is powertrain cooling. Hi, Mike. Good to see you again.
Hi, Kevin. Good to see you too. Yeah, we're looking at cooling systems, although they tend to be called cooling systems. More accurately, they are thermal management systems, because a huge proportion of vehicle engineering is thermal management, so cooling and warming. It applies across the car, so every part that moves has to be lubricated in order to reduce friction. But really, when we talk about cooling systems, or what people would think of as cooling systems, we're talking about the powertrain and the cabin. So in this episode, we're going to talk about the powertrain cooling systems.
Right. So just to take that in detail, then, with engines, the heat is not just caused by friction.
Yeah, that's right. So you have moving parts that have to be lubricated, otherwise they would cause heat. But actually, in an internal combustion engine, and we'll come to the electric vehicles later, but an internal combustion engine, you have ignition of the fuel-air mixture. And it's ignited under very high pressure, and so it can have temperatures of 1,500 to 3,000 degrees Celsius. So a cooling system is needed in order to keep that temperature in a stable range. So
by removing excess heat from the system?
Yeah, exactly. Removing excess heat from the system. Right. So it's generating heat. Some of that heat is necessary, but it has to remove excess from the system.
Okay. So what was the first car with a cooling system?
The very first car, actually. So the Benz Motorbike, 1885, that had what was called a thermal siphoning cooling system. In fact, the patent that Benz wrote for that car had the line, the engine is kept at a steady temperature by the evaporation of water. So in that very first car.
Okay, so we are familiar then with water being pumped through the engine back into the radiator to be cooled. So what is thermosiphoning?
Thermosiphoning, it's still a circuit of water that's passing through the system. It's still passing through the engine block, but it doesn't have a mechanical or hydraulic pump actively pumping it. So as water heats up, it rises, and as it cools down, as it cools in temperature, it drops back down again. So a thermal siphoning cooling system uses that natural expansion and rising and condensation and dropping to create a natural circuit, so it naturally circulates itself through the system.
All right. So no pump. So did it work? Was it effective?
Yeah, it was reasonably effective. Now, not effective in terms of what we would think of cooling system needs to do today, but in terms of the operation of cars in sort of the 1900s and into the teens, it was reasonably effective. So Ford Model Ts, they all had thermal siphoning systems on them. So what you find with thermal siphoning is that it's good for most of the operation of the car, but then it could overheat if the car was worked too hard, was pushed too hard. And a common reason for that is it's asking, it's the physics are making the fluid circulate, the water circulate through, but because it's not being pumped, you have different local pressurizations and different local flow rates. So you couldn't always be sure that you were getting the same flow of water to all parts of the engine equally, and that was the common reason for the overheating.
So you might get, I think what the term might be, a hot spot. You get hot spots in various points in the system.
Yeah, that's exactly right. Yeah.
Okay. So is that when the water pump come in? Is that the next stage?
Yeah, it is in terms of progression of the cooling system. But the funny thing is the water pumps were in existence already at that point. Just they weren't very good. So they had a lot of problems sealing water pumps. In fact, actually, the Ford Model T, the very first Ford Model Ts, the first few hundred of them, actually were made with water pumps. But they were so ineffective. They were leaking so much that they took them off and went back to a thermal siphoning system.
Right. So I never knew that. That's interesting. So what about heating the engine up in cold weather?
Okay, so if we talk about the pump system, so the very first cars then, they had pumps on, the pumps were working, but the problem with those pumps was that they were permanently on, so as soon as the engine was running, those pumps were circulating. And then that was a problem in cold weather because they're cooling the engine down. The engine does need to warm up. It needs to get to a stable operating temperature. And the pumps had a tendency to hold that back. So then the first car that had a thermostat was the 1914 Cadillac V8. And that thermostat, that changed then how smart the cooling system was. So what a thermostat does, effectively, it's a valve that opens automatically based on the temperature of the water. And when it opens, what it does is it shortcuts the circuit. So it effectively takes the radiator out of the loop. So the cooling circuit goes locally through the engine. When the engine is up to temperature, it's warmed up, then closes, and then it goes on a longer loop, and it's now actively cooling it because the water is circulating through the radiator.
Yeah, so it was a fairly simple solution. But I would say in those days, early days, water freezing was a problem.
Yeah, absolutely, because the very first cars were just pure water.
Yeah.
Water is very good at accepting heat, right? So it's very good at rejecting the heat from the system, but it's got a limited range. So its operating range is from 0 to 100 degrees C. And also when it freezes, it expands. So in low temperatures and very high temperatures, bearing in mind, low ambient temperature is often below 0. And the operating temperature of the engine is often in the 80, 90 degrees C. So it's already getting up close to that boiling point. So in terms of the low temperature, then scientists were then looking for a way to stop the water from freezing. And ethylene glycol had been invented, 50 years before the car was invented. And it was already known that when it was mixed with water, it lowered the freezing temperature. Actually, it raises the boiling temperature a little bit as well. It wasn't widely used. So it was kind of one of those substances that had been invented. And then in World War I, it was discovered that in the production of dynamite, it could be used to create dynamite that could operate in cold weather. So suddenly the production of ethylene glycol, increased dramatically in World War I. And then it became readily available and started to become something that could be added into vehicles. And then in 1927, there was a US company called Prestone, and they became the first company to create the first non-flammable ethylene glycol, because obviously that dynamite effectiveness is not something we want in the engine.
Not really. So antifreeze then, a big step. What was the next big step? What did it take on?
Next thing that happened then, the next big step, is a really small component that's on every vehicle that has water cooling system in it, and nobody really pays any attention to it. And yet it actually, it transformed what cooling systems could do. So the temperature of the water rises and falls, so does the pressure, and so does the expansion of the water. So in the early days, it was really common to see cars parked at the side of the road, steam bellowing from under the hood, all the classic movie scene. And the water had to be topped up frequently, because when that steam bellows away, that's losing water from the system. Now, it was well understood that if the system could be sealed and pressurized, then the temperature, the boiling temperature, could be raised. So that's just a basic physics phenomenon, that at a higher pressure, the boiling temperature is higher. The problem with sealing a system is that you're pressurizing it and it's changing in pressure. So it could very quickly, in an overheating scenario, have a very dangerous level of pressurization.
You have a bomb under the hood, as well as the petrol.
Exactly, basically. So, and then in 1939, then we have the part that everybody would think about, but nobody, everybody knows, but nobody would think about, which is the pressure radiator cap, or the pressure cap.
Oh.
And that was first used in 1939. Buick actually were the first company to put it onto their Series 40 car. And what a pressure cap does is it is set to release at a certain pressure point. So as the system increases in pressure, if it reaches that point where it could reach those dangerous overpressurization levels, the pressure cap releases the excess pressure. So it just always maintains the temperature and the pressure in a safe working region. The other smart thing a pressure cap does is it also lets air back in to compensate for the fact that volume has been lost from the system.
Yeah. You won't get the airlocks or whatever it's going to be.
Yeah, that's right. And so the pressure cap still used today, but it absolutely revolutionized how effective cooling systems could be.
Okay. And then presumably that not a problem for an air-cooled car.
No, right. And again, so a few episodes ago, we spoke about air cooling in relation to the aerodynamics. And in the first 50 years of the last century, we saw a lot of cars like the 911 that was air cooled. Now, so air cooling works by passing the air directly over the engine. So in a water cooled system, the air passes through the radiator. So in an air cooled system, the air passes directly over the engine and extracts that heat. The first car that we see in production, in mass production, with an air cooled engine was Tatra. Again, you might remember a company we came across in our aerodynamics conversation, and they produced the Tatra Model 11 in 1923.
And was that a rear engine, a front engine car?
No, it was rear engine, right? So, yeah, I see where you're going with that. So we had talked about the Tatra 77 that was rear engine, right?
Yes.
So the 11 was front engine. The 77 then that we talked about previously, that was rear engine. Yeah. And we talked the last day where there was that strong link between the aerodynamics promoting engines to the rear and then becoming air cooled.
So VW Beetle, Porsche 911, that sort of. So what else is air cooled?
Yeah, there were lots of air cooled cars in the the first 50 years. Tatra, their entire range nearly was air cooled right up until of cars right up until 1999. So they produced the 700 was their last car in 1999, and that was an air cooled engine. Porsche 356, Porsche 911, in the States with the Chevrolet Corvair. So they're probably a little bit exceptional in that they're higher end vehicle sports cars. What was really common was for small cars, small cheap cars, sort of mobility for the masses, for those cars to have air cooled. So Volkswagen Beetle, Volkswagen Type 2, Volkswagen Type 4, all of the Trabants, 500, 600, 601, the Citroen 2CV, the Fiat 500, the NSU Prinz. So over and over again, these quite often in Europe, these small European cars, small cheap European cars were air cooled and quite often rear engine.
And what about now in 2022? Does anyone produce air cooled engines today?
Tatra still are in existence. They're a truck company, and they still produce an air-cooled V8, actually, for one of their trucks, a diesel air-cooled V8. Predominantly where we think about air cooling now is in motorbikes. So motorbikes have the advantage of the engine hanging out in air, so there's a lot of natural airflow over them.
And what are the pros and cons of air cooling?
They're lighter. Because you don't have all of that water system running around, and they're less complex. You don't have to try to seal that water in. So there's fewer components in them as well. So they can be cheaper to make as a total system, although the engine itself can be more complicated to make because the castings have to have fins, or they often have fins sticking out to try to capture that cold air. But the big problem with air cool, as you can imagine, is overheating when you push them very hard.
Yeah.
So with an air-cooled car, if it's running in slow traffic and heavy traffic, or if it's at higher ambient temperature, or even if it's working hard, let's say going up a mountainside, so you've got lower levels of air pressure and you're working hard, in those sort of scenarios, air-cooled engines can be problematic. Quite often, there was a large engine-driven fan bolted onto the side of the engine, but they were a big performance draw as well.
Because you would often see, well, I've seen it once where the Fiat 500 Abarth with the rear bonnet open to increase cooling on special struts, and
brilliant example. That's right, the 500S, the sports version of it. They had to actually keep the hood open permanently on struts, and that was their very cheap and very effective way of getting extra cooling into that engine. Yeah.
Excellent. So performance is the reason that we don't see air-cooled engines anymore. Would that be fair to say?
It was a factor, but it's actually not the main reason. The main two reasons were noise and tailpipe emissions. So the water jackets that run in water-cooled engines create sound are sound barriers. They are sound insulators in their own right. But much more than that, the tailpipe emissions of air-cooled engines are generally worse than water-cooled engines. And that's because with a water-cooled engine, you can control much more accurately and more specifically the combustion chamber. So the combustion chamber is where the ignition takes place in the engine. You can control much more accurately and specifically the temperature within that combustion area. And having a controlled temperature means that things like the compression ratio can be increased. So the compression ratio, in simple terms, is how much the volume of fuel air is compressed within the engine. And that can be increased. It can run at higher pressure and therefore can run more efficiently. So you have this cumulative effect where you can make the engine generate more power, but also be more efficient and more fuel economical. And that wasn't available to the air-cooled engines because they just didn't have that detailed control of the temperature in the engine. So, which is why with motorbikes now, we see that motorbikes, most big engine motorbikes or larger engine motorbikes are now water-cooled.
All right. And what would have been the first water-cooled motorbike?
There were a few attempts in the 1920s, 1930s, but the bike that we tend to think of as the first mass-produced one was by Suzuki in 1971. So it's the GT750, which was affectionately known as the Kettle, or I think in the US it was known as the Water Buffalo.
Okay, so we've talked, actually and I'm thinking the reason I paused there, I think I have a GS850 myself and it's air-cooled, and it's the next model after that, so there you go. So we've talked about heat and cooling petrol or diesel powertrains. So there's a common misconception about the powertrain of electric vehicles don't need to be cooled, Mike. So why is this?
Yeah, it's a funny misconception, as you say, that is out there, Kevin. I think it comes from just very simply the fact that EV cars have a styling at the front that we talked about it in the styling and indeed in the aerodynamics conversation, where that front fascia is closed in, so there's a smaller grille opening and it's down low, and I think that then leads to people thinking that actually they don't need cooling. Now, electric vehicles certainly reject heat and they certainly need to be cooled. There's less total rejected heat energy than there would be on a combustion engine, but often the cooling circuits are more complex. There's more individual cooling circuits. So why are electric cars cooled? Well, when electrical current passes through any material, any conductive material, it generates heat because of the resistance. And then that resistance in turn creates heat. The heat creates resistance. It's an invertuous circle. So in order to maintain operating performance, the temperature does need to be managed on all electrical components. For many electrical components, that can be done through air cooling, but then and sometimes in cars we see water type cooling.
Okay, so just like a petrol engine, cooling the electric and electronic components improves performance. So with that in mind, why do EVs have to have more individual circuits? Yeah,
they do have to have more individual circuits. So with the combustion engine, the temperature that's being rejected, it wildly fluctuates from the very high peaks to the lower operating temperatures. So there's a lot of heat energy that's extracted. But at the same time, the combustion engine can operate across a wide band of temperature. The electronic components, they do not reject as much heat, but they need to be maintained at a much narrower band of operating temperature. And that results then in the different electronic components needing to have different cooling circuits because they're just operating in different temperatures. So typically in an electric car, the drive motor and the balance of plant equipment like the inverter or the DC-DC converter, they operate at a similar temperature point around 50 to 60 degrees Celsius. And that's not unlike a combustion engine. And actually, similarly, they're often cooled using a liquid cooling circuit. The traction battery, the large battery in an EV, that has an operating temperature around 30 degrees Celsius, sort of around that temperature. Because it's a lower temperature, it has resulted in a number of different approaches. Sometimes they're water cooled or liquid cooled, just like the other components, and then sometimes they're air cooled.
So it's not unlike the conversation we had earlier about air-cooled or water-cooled engines.
Yeah, very like it actually. In fact, the same pros and cons start appearing as well. So batteries have the disadvantage of the weight, the complexity, and the sealing of the cooling circuit. Air-cooled batteries don't have those extra components, but they're also harder to maintain at an optimum temperature when they're working harder or they're in higher ambient conditions. And actually a little bit like the powertrain conversation, we tended to see more air-cooled batteries earlier in EV development than we see now. So a little bit like the air-cooled engines. So the first hybrids tended to be all air-cooled batteries. So the likes of the Toyota Prius has an air-cooled battery. The early EVs, particularly the smaller ones like the Nissan Leaf, also has an air-cooled battery. Tesla has always used water-cooled batteries, larger engine, and the Nissan Leaf still maintains an air-cooled battery. But when Nissan moved the powertrain and the battery from the Leaf to the ENV200, which is their van, it was now working harder. So although the battery is still air-cooled, they now sub-cooled the air using the air conditioning system from the cabin.
Right. So with the Prius being a hybrid, hybrids then must have cooling systems for both the EV element and for the internal combustion element. Would that be fair to say?
Yeah, absolutely. Yeah, so they basically double up on the complexity. If you take an example of Mitsubishi Outlander PF, so one of the most popular plug-in hybrids that's out there. So it has a water-cooled engine, as you would expect.
Yeah.
It has the HVAC system for the cabin, so the heating, ventilation, air conditioning system for the cabin. It also has an oil-cooled front motor, electric motor. It has a water-cooled rear motor. It has a separate air conditioning system to cool the battery. And in some applications, there's an option of a water heater for the battery as well. And each one of those is a separate cooling circuit.
That's an incredible amount of complexity in cooling. That's what?
Just in cooling.
5 or 6 shapers. That's absolutely incredible. Yeah. So EVs are cooled in a similar way to internal combustion cars, which is a surprise to me.
Well, so they have been, and now we're starting to see development on that. So what we're starting to see now more and more is the use of the heat pump. So a heat pump, similar principle to what you would have maybe in a house, if your house has a heat pump. Effectively, it's an air conditioning system in reverse. So in this case, it's taking heat energy. So in an air conditioning system, it takes heat energy from the cabin, for instance, and rejects it. In this case, it's taking heat energy from the cooling system, but it's reversible, so it can be used for heating the system up or cooling it down. And what we see now is that heat pump system is becoming more and more intrinsically linked to the cabin cooling, because that also has an air conditioning system. So actually, we're going to talk about that in a lot more detail in the next episode when we look at cabin cooling.
Excellent. That was great, Mike. Very interesting. And in our next episode, we're talking about cabin cooling. Thank you for joining us today on the Talking the Talk podcast. My thanks to Mike Keane, and you can check out his consultancy on mikekeane.ie. Then check out irelandmade.ie to view our back catalogue of videos celebrating stories of Irish transport, past and present. We look forward to welcoming you onto our next episode, where we further explore the origins of automotive technology. You can find us on YouTube or Spotify or wherever you get your podcasts. Please subscribe and tell your friends. Bye for now.